Welcome, curious minds, to the Deep Dive. Today we're setting out on an incredible exploration of our home planet. We've gathered a treasure trove of sources, articles, research, expert insights to take you on a journey from Earth's fiery core right up to its highest atmosphere and, across its amazingly diverse landscapes.
Yeah.
Think of this as your shortcut to understanding the big picture. We'll definitely hit some surprising facts along the way.
And our mission today is really to connect those dots for you. It's fascinating, isn't it, how all these elements of our planet,
Yeah.
the colossal geological forces shaping continents, the intricate atmospheric movements driving our weather, and of course, human activities influencing everything. They aren't isolated at all.
Not at all.
They're part of one grand dynamic system. We'll be synthesizing these geographical concepts to give you a truly holistic understanding, looking at the why and how behind these connections, and crucially, why they matter to your daily life.
Absolutely. By the end of this deep dive, you'll have a comprehensive yet completely digestible overview of our planet, packed with those aha moments and real-world relevance. You're about to get truly well-informed about our amazing Earth without getting bogged down in jargon. So let's unpack this and jump right in.
Let's do it.
Okay, let's kick things off with a fundamental distinction, something we often mix up. Climate versus weather. If we're going to understand our planet's atmospheric systems, what's the core difference we need to grasp?
That's the perfect starting point. Think of it this way. Weather is like your daily outfit. It's what you experience right now.
Okay.
Or what you'd see if you looked out the window. It's the short-term, day-to-day atmospheric conditions influenced by immediate temperature and pressure.
Right.
Climate, on the other hand, is your entire wardrobe. It's the average of all your outfits over decades, typically averaged over 30 years or more, giving us the expected conditions for a region.
So the long game versus the snapshot.
Precisely. And the very air we breathe today, that amazing wardrobe, it didn't just appear overnight. It's the product of millions of years of Earth's evolution.
Millions.
Yeah. In its earliest days, our planet's atmosphere was incredibly thin, mostly hydrogen and helium, completely unbreathable.
Wow. So the air we rely on, the very essence of life, is a testament to deep time and active planetary forces.
Yeah.
It's been completely transformed. Then did we go from a hydrogen-helium soup to the air we know now? Here's where it gets really interesting.
It's a fantastic story of planetary alchemy, really, driven by a dual process, both geological and biological forces.
Okay.
Geologically, think of it as Earth exhaling, massive volcanic activity, and the gradual release of gases from the planet's interior.
Degassing.
Degassing, exactly. That built up the early secondary atmosphere. But then, crucially, life itself entered the scene. The emergence and evolution of living organisms, particularly through processes like respiration, early life forms consuming gases and releasing others, and critically, photosynthesis. Plants, yeah. Starting to absorb carbon dioxide and pump out oxygen. That fundamentally reshaped the atmosphere. It was this massive feedback loop, creating the oxygen-rich air that allowed complex life to flourish, a stark contrast to the barren early Earth.
That interaction between the living and non-living world created our breathable air. It's more than just oxygen and nitrogen, though, isn't it? What else is floating around up there, and how much can it change from place to place?
You're right, it's a complex soup. Our atmosphere is a physical mixture of various gases, tiny dust particles, water vapor, aerosols.
It links together.
Yeah, and while it behaves like one giant envelope, each component retains its individual properties. That's key for everything from breathing to, chemical reactions like fire. The big players making up the vast majority are nitrogen at about 78%.
The 70.
And oxygen at 21%. Then you have argon, a noble gas, around 0.93%. And carbon dioxide, which despite its tiny percentage, only about 0.03%, plays a colossal role.
Tiny but mighty.
Absolutely. Beyond these, there are trace gases like ozone, which makes up an almost infinitesimally small part, 0.000004%, but is critical for life. But here's the really variable part. Water vapor.
Humidity.
Exactly. It can swing wildly from almost zero in extremely dry deserts to maybe 4 or 5% in steamy equatorial rainforests. And its presence is fundamental to all our weather.
So we have the building blocks, but then there's the stuff we don't want, right? The pollutants and aerosols, things we add.
Exactly. These are the additions that become problematic, often stemming directly from human activity. We're talking about particulate matter, like these incredibly tiny airborne particles.
PM 2.5, PM 1.
Precisely. So small, they're measured in microns. They're a serious health concern because they can bypass our body's natural defenses, get deep into the lungs, even into the bloodstream, potentially causing long-term damage.
Scary stuff.
It is. Then you have sulfurous and nitrous gases, carbon monoxide from incomplete combustion, like car engines, dust from construction or natural dust storms, and aerosols, those suspended volatile substances, like the compounds that carry smells from cooking or perfumes. The key here is that the levels of these pollutants and aerosols are directly influenced by what we do on Earth. It's a direct reflection of our footprint.
It's a delicate balance then, and it sounds like we're actively tipping it with our emissions. But not all gases are created equal when it comes to regulating our planet's temperature. Some of these trace gases, like CO2, have an outsized impact, right?
That brings us to the absolutely vital greenhouse effect. Picture this. Without gases like carbon dioxide and other greenhouse substances, which collectively make up less than 1% of our atmosphere.
Less than 1%.
Yeah. Without them, Earth's average temperature would plunge to a frigid negative 18 degrees Celsius. Our planet would be a frozen, lifeless ball.
But
these gases act like a thermal blanket, trapping just enough solar radiation to maintain our average ambient temperature at a pretty comfortable 15 degrees C, making life as we know it possible. The nitrogen and argon, while abundant, actually serve a diluting purpose. They prevent our oxygen-rich atmosphere from, well, spontaneously combusting under solar radiation.
Okay, that's a crucial balance. But the post-industrial revolution era changed everything for that balance, didn't it, since around 1750?
It did, dramatically. Since around 1750, we've seen a sustained, massive increase in carbon dioxide emissions, a growing carbon footprint. This surge in greenhouse gases, even though they still make up such a small fraction of the atmosphere, is the primary driver of global warming and climate change.
Then we see extreme examples of this elsewhere.
Absolutely. Look at Venus. Its atmosphere is about 90% carbon dioxide. It's a superheated, supercharged planet with surface temperatures hot enough to melt lead. It's a stark illustration of a balance gone catastrophically wrong.
And this isn't just theoretical science.
Not at all. It's our reality. 2023, for example, was the hottest year on record since tracking began. Global average temperatures exceeded pre-industrial levels by around 1.18 degrees C, impacting both air and ocean surface temperatures. That's a huge shift in geological terms.
So what does this all mean for us? It means understanding these invisible forces is more critical than ever, especially when we consider how temperature plays out not just across the globe, but even at different altitudes. The atmosphere isn't just a uniform blanket, it's layered, like a giant protective onion.
That's a great analogy. The atmosphere is indeed stratified into distinct layers, each with unique characteristics and temperature trends. Even though all the gases are mixed, they behave according to the properties of their layer. Starting from the surface, we live in the troposphere.
Where we are now.
Exactly. It extends up to about 13 kilometers. This is our world's weather factory. All our rain, wind, storms happen here. And crucially, temperature decreases as you go higher in this layer.
So it gets colder as you climb a mountain. Makes sense. What's next?
Above the troposphere is the stratosphere, reaching up to 50 kilometers. Now here is a twist. Temperature actually increases with height.
Increases? Why?
Because this layer contains the vital ozone layer, typically between 20 to 25 kilometers. It absorbs harmful ultraviolet UV radiation from the sun, and that absorption process heats up the surrounding air. It's our planet's natural sunscreen.
Okay, vital.
Absolutely. Next, we ascend into the mesosphere, up to 80 kilometers. Here, temperatures drop again quite significantly, and this is where meteors often burn up those shooting stars we see. Beyond that, the thermosphere. Temperatures here soar due to intense solar radiation absorbing X-rays and UV, and it's important for communication, reflecting radio waves. Finally, the exosphere is the outermost layer, gradually thinning out into the vacuum of space.
And the boundaries between these layers?
We'll call them pauses, like lids on the atmospheric onion. So you have the tropopause, stratopause, and mesopause marking the transitions.
It's like our Earth has its own layered defenses and temperature regulators, each with a specific job. But what causes these incredible temperature variations on the surface? And how do they influence everything from our local climate to the giant unseen movements of air and water across the planet? #2, global air and ocean circulation.
Right. The Earth's temperature patterns are far from uniform. They're constantly modified by a number of factors. First, consider location, continental versus coastal.
Okay.
Take a city like Delhi, far inland. It experiences extreme temperatures, scorching summers, biting winters. Why? Because land has a low specific heat capacity. It heats up and cools down very quickly. Compare that to a coastal city like Mumbai or Chennai. The vast ocean, with its high specific heat capacity, acts like a giant temperature regulator. It moderates the extremes, leading to much milder seasonal variations.
So the ocean acts as a natural air conditioner in a way. What else impacts temperature? Altitude.
Altitude is another powerful modifier. It often mimics the effect of moving towards the poles. Mount Kilimanjaro is a fantastic example.
Near the equator, right.
Exactly. Just 3 degrees south of the equator, a typically sweltering tropical region. Yet its peak, around 6 kilometers high, is permanently snow-capped because temperature drops dramatically with height, even in the tropics.
Makes sense. And ocean currents.
Profoundly influential. Warm currents bring positive temperature anomalies, making areas warmer than their latitude suggests. Cold currents do the opposite, leading to negative anomalies, making them cooler. And of course, local winds can have a dramatic impact.
And then there are winds. We feel them every day. But some are truly remarkable in how they affect local weather, aren't they? Specific named winds.
Absolutely. Think of the warm winds like the Chinook in North America, the Fohn in Europe, or the Lu in India, known for their warming, often drying effects, sometimes melting snow rapidly.
The snow eater, the Chinook.
Exactly. On the flip side, you have chilling cold winds like the Grigale in Greece, the Meltem in Turkey, the Bora in Albania, the Buran in Siberia, or the infamous blizzard in Canada. One particularly intriguing example is the Mistral in France.
Ah, the Mistral.
Yeah, it's a powerful drainage wind that sweeps down mountain slopes on cold, clear nights. As the land loses heat rapidly, the air touching the slopes cools, becomes denser. This cold, heavy air then rushes down the valleys.
And that impacts things like farming.
Hugely. It can be very damaging to viticulture grape growing, which is why you often find traditional hill station communities built on the sides of mountains, not directly on the valley floors where these winds concentrate. Fun fact, the high-performance Bugatti Mistral car is actually named after this powerful wind.
Interesting. So if the Earth is constantly trying to equalize pressure and temperature across the globe, how does air actually move across the planet? Why doesn't it just go in a straight line from high to low pressure?
That straight line is where Earth's rotation plays its trick. Imagine you're on a spinning merry-go-round,
Okay.
and you try to throw a ball straight across to someone. From your perspective, the ball seems to curve, right? That apparent curving force is exactly what the Coriolis force does to moving air and water. It's not a real force pushing the air. It's an effect caused by the Earth spinning beneath the moving air mass. This deflection causes winds and ocean currents to turn to the right in the northern hemisphere and to the left in the southern hemisphere.
Wow. Okay. So it just looks like it's curving.
Precisely. But that appearance fundamentally shapes global weather patterns and oceanic circulation.
That's such a great analogy. The merry-go-round makes it so much clearer. So this apparent force fundamentally shapes global weather patterns, and its effects are amplified way up in the upper atmosphere, leading to something truly fascinating. Giant atmospheric waves and incredibly fast rivers of air.
Indeed. Up in the upper troposphere, influenced heavily by this rotational effect, the westerlies, those winds blowing generally from west to east, don't follow a straight path at all. Instead, they adopt a distinctive wavy pattern. These large-scale meanders are known as Rossby waves.
Rossby waves.
Yeah, and what's particularly interesting is how these waves tend to intensify as they move towards the poles. The impact of Rossby waves is profound, especially for the much variable weather of the mid-latitudes.
Like the UK.
Exactly. Think of the classic British type of climate. 1 minute it's sunny, the next it's pouring rain. This unpredictable, intermittent rain, with sudden shifts between low and high-pressure conditions, is a hallmark of Rossby wave activity. We saw this vividly during the 2019 Cricket World Cup, for instance. Matches were frequently interrupted by these sudden, localized downpours driven by these waves.
Right, I remember that. And embedded within these huge waves are those incredibly fast rivers of air we call jet streams, right? Like superhighways in the sky.
Exactly. Jet streams are narrow bands of very fast-moving air, often reaching speeds of 300, 320 kilometers per hour, that snake their way within these larger Rossby waves.
How are they even discovered?
It was actually during World War II. Pilots flying long distances, say between New York and London, noticed significant differences in flight times and fuel consumption depending on their direction. Flying with a jet stream could dramatically cut travel time, while flying against it was a major struggle, burning much more fuel.
Ah, practical discovery.
Very much so. Today, we classify them into permanent jet streams, which are always present, and seasonal or temporary ones, which shift with the changing seasons.
This raises an important question. How does all this atmospheric dance translate into something we can physically see and feel on the ground, like rain? But before we get there, let's explore how similar forces drive massive movements of water in our oceans, the ocean currents.
Ocean currents are truly the planet's circulatory system, moving vast amounts of heat around the globe.
Yeah.
They're primarily driven by two familiar factors: the push of wind on the surface and the subtle deflection of the Coriolis force.
Same players, different medium.
Exactly. Secondary influences, like differences in salinity and temperature, also play a role by affecting water density. A unique global current, for instance, is the west wind drift.
Around Antarctica.
Yes, a powerful current that almost completely circumnavigates Antarctica. It flows largely unimpeded because there are no major land masses in the way, constantly driven by the persistent southern westerlies.
So we often hear about these massive rotating gyres in the oceans.
Yeah.
Is it just that the wind causes the water to spin around in a circle? Seems too simple.
It's far more intricate than a simple spin, and it involves a fascinating phenomenon called the Ekman spiral.
Ekman spiral. Okay.
When wind blows over the ocean, it imparts a fraction of its energy, only about 4% to the surface layer of water. But because of the Coriolis force, this top layer doesn't move directly with the wind. Instead, it gets deflected about 45 degrees to the right of the wind direction in the northern hemisphere.
45 degrees. Okay.
Yeah. The layer of water beneath that then gets deflected further to the right, and the layer below that even further, and so on, with decreasing speeds as you go deeper. This creates a spiraling effect down through the water column.
So it twists as it goes down.
Right. Now, the net overall water transport, combining all these layers, is approximately 90 degrees to the right of the wind direction in the northern hemisphere. That's called Ekman transport.
90 degrees. That's a huge shift in direction from the wind. So this net movement, Ekman transport, is what creates those massive rotating gyres.
Precisely. This persistent Ekman transport causes water to slowly pile up in the center of ocean basins, forming a slight, almost imperceptible dome of higher sea level. This subtle elevation creates a pressure gradient. And it's this pressure gradient that then initiates and drives the large-scale rotating gyres we observe in each hemispheric ocean. It's a fundamental mechanism.
And does this explain why some currents are stronger than others?
It does. Ekman transport also explains western intensification. Currents on the western side of ocean basins, like the famous Gulf Stream in the North Atlantic, are much stronger, narrower, deeper, and faster than their eastern counterparts. This intensification is due to a complex interplay of the Coriolis force, the Earth curvature, and friction.
And within these gyres, you get unique areas.
Yes, like the Sargasso Sea within the North Atlantic Gyre. It's this unique, calm, clear, warm water pool known for its floating sargassum seaweed. Also, to balance the water that gets piled up in the western parts of ocean basins by the trade winds, there's a fascinating subsurface current called the counter-equatorial current, CEC. It flows in the opposite direction, east to west, typically just 1 to 3 meters below the surface.
It's incredible how many forces, visible and invisible, shape these massive movements of water. Let's zoom in on a couple of specific examples, starting with the North Atlantic. How does it flow there?
Okay, in the North Atlantic, the primary flow is the North Atlantic equatorial current moving westward. As it approaches the Caribbean islands, it splits. You get the Antilles current flowing north of the islands and the Caribbean Chiani current entering the Caribbean Sea. These then converge to become the powerful Florida current, which is essentially the birth of the mighty Gulf Stream, carrying immense warmth towards northern Europe.
A real heat conveyor belt.
Oh, absolutely. Now, the North Indian Ocean presents a unique and utterly fascinating case because its currents are entirely monsoon dependent. They completely reverse direction with the season.
Completely reversed. That's truly unique.
Yeah.
So how does the monsoon manage to reverse ocean currents?
During the monsoon months, specifically the southwest monsoon, our summer, a clockwise gyre forms along the coasts of India and Africa. The North Indian Ocean equatorial current is strong and flows east to west. This also leads to the formation of the powerful Somali current along the African coast, which brings significant upwelling of cold, nutrient-rich water.
Okay, clockwise in summer.
Right. But in the non-monsoon months, our winter, when the northeast trade winds dominate, the entire pattern flips. The gyre's rotation switches to anti-clockwise. The North Indian Ocean equatorial current reverses its direction, flowing from west to east, and consequently the Somali current along the African coast also reverses.
Wow.
This complete seasonal reversal makes the North Indian Ocean a singular and dynamic example of monsoon-driven oceanography. It's a clear, powerful connection between atmospheric and oceanic systems.
These currents don't just move water. They distribute heat, influence ecosystems, and crucially, even impact rainfall. Speaking of which, how exactly do we get rain, and why does it vary so much across the globe?
Whether rainfall actually occurs isn't just a random event. It depends predominantly on two crucial factors:
Right.
relative humidity and the specific latitude of a place.
Okay, humidity and location.
Exactly.
Sure.
Think of relative humidity, RH, as how full the air is with moisture. It's a percentage that tells us how close the air is to its saturation point, to actually dropping that moisture as rain. And that fullness isn't just about how much water is there, but how much more it could hold, which changes drastically with temperature. Hot air can hold vastly more moisture than cold air.
Okay, so it's relative.
Precisely.
Yeah.
To really illustrate this, let's compare two very different places: Singapore and Dubai. Singapore, right on the equator, experiences intense vertical convection. Its air is often nearly saturated, and because the air itself isn't extremely hot compared to a desert, its capacity to hold moisture is relatively limited. So in Singapore, you can often get heavy precipitation, even with relative humidity at maybe 60–70%, because the rising cooling air quickly reaches saturation.
That makes sense. Hot air rises, cools, can't hold the water, rain. But in a place like Dubai, even really high humidity often doesn't mean rain, right? What's the difference there?
Exactly. Now, imagine Dubai, a tropical hot desert. Even if its relative humidity reaches a seemingly high 80–90%, it often doesn't rain. Why? Because Dubai is typically under high-pressure systems, meaning air is sinking, not rising, and the air is intensely hot and desiccated. Hot air has a much, much higher capacity to hold moisture. So even with a high percentage of moisture relative to its capacity, the absolute amount of moisture needed to fully saturate that very warm air and initiate condensation is far, far greater.
Okay, so the air just isn't getting full enough, even if the percentage sounds high.
That's the key insight. Humidity alone isn't enough. The air's capacity to hold water, heavily influenced by temperature, pressure, and latitude, is the real game changer.
That's a fantastic aha moment, showing us that humidity alone isn't enough. It's about the air's capacity. So once that capacity is reached, saturation occurs. What actually happens then to form rain?
Once the air reaches that saturation point, the primary mechanism for rainfall is condensation. As the air cools, its moisture-holding capacity diminishes, forcing the invisible water vapor to convert into visible liquid droplets or tiny ice crystals.
Okay.
But these tiny droplets or crystals aren't just floating randomly, they need something to cling to. Microscopic dust particles, pollen, salt crystals from the ocean, spray, these act as what we call condensation nuclei.
Little seeds for raindrops.
Exactly. The water or ice builds up around these nuclei, colliding and coalescing, growing larger and larger until they become too heavy to remain suspended in the atmosphere by air currents. At that point, gravity takes over, and they fall as precipitation, rain, snow, sleet, or hail.
And looking up at the sky, different cloud types give us clues about what kind of weather to expect, don't they? They're not all just fluffy white things. They tell a story.
You're absolutely right. Clouds are incredibly descriptive. Cumulonimbus clouds, for example, are those towering, dark, anvil-shaped giants we associate with thunderstorms.
The big stormy ones.
Yeah. They bring a heavy, often short-duration downpours, frequently with hail, lightning, and strong winds. Then you have cumulus clouds, the classic fair weather clouds. They look like fluffy, white packs of cotton wool. While they don't typically cause rain, they add immense aesthetic beauty to the sky.
The puffy ones.
Right. Higher up, you'll see cirrus clouds. These have a delicate, wispy, or feathered look. They're composed entirely of ice crystals, often appearing shiny, and usually indicate fair but possibly changing weather.
High and thin.
Exactly. Finally, stratonimbus clouds, sometimes called nimbostratus, are those dark, gray, low to middle level, continuous sheets of clouds. These are the ones that bring light to medium rainfall over long periods, the kind typical of a persistent drizzle or a monsoon day. Each cloud type really does tell a story about the atmospheric conditions above us.
From a wispy feather in the sky to a full-blown monsoon, these cloud types tell us so much about the weather to expect. But there's more than one way for rain to fall, isn't there? The way it's triggered can be quite different depending on the situation.
Indeed, there are three primary types of rainfall, each initiated by distinct atmospheric processes that cause air to rise and cool. First, convectional rainfall. This is what you often experience on a hot summer afternoon, or very commonly in equatorial regions. Intense solar heating warms the land, causing the air directly above it to heat up, become less dense, and rise rapidly.
Hot air rises.
As this warm, moist air ascends, it cools and expands. That's called adiabatic cooling. Its moisture-holding capacity decreases, it quickly reaches saturation, condensation occurs around dust particles, and then often suddenly you get a heavy but typically short-duration, highly localized downpour. Think of a sudden summer thunderstorm.
Got it. The sudden heavy downpour we often experience. What are the other types, perhaps more linked to geography, like mountains?
The second type is exactly that: orographic or relief mountain rainfall. This happens when moist air, often blowing in from an ocean, is forced to rise as it encounters a mountain barrier. As the air is pushed upwards along the slope, it cools adiabatically, condenses, and releases its moisture as rain, predominantly on the windward side of the mountain, the side facing the wind.
And the other side.
The air that descends on the leeward side, having lost most of its moisture, is now dry. As it sinks, it compresses and warms up, creating a rain shadow, a much drier area on the sheltered side of the mountain range.
Okay, makes sense. And the third type?
The third is frontal rainfall, which is typically associated with mid-latitude weather systems, specifically cyclones or depressions. These occur when a large mass of warm air meets a large mass of cold air. Since warm air is lighter and less dense, it's forced to rise over the colder, denser air mass along a boundary called a front. This lifting causes the warm air to cool, condense, and produce widespread, often prolonged, rainfall along this front where the two air masses interact. Each type gives us a different clue about the atmospheric dynamics at play.
Understanding these mechanisms helps us predict everything from a sudden downpour to a prolonged monsoon. Now, let's shift from the dynamic sky to the solid ground beneath us and explore how our planet itself is structured and formed, starting with its very building blocks, geology time.
Absolutely. Right. When we talk about Earth's composition, it's vital to understand that our planet is not just a uniform hunk of rock. Not at all. Instead, it's beautifully stratified, with elements arranged largely by density.
Denser stuff sinks.
Exactly. The heavier elements are concentrated at the center, and progressively lighter ones are found outwards. Looking at the Earth as a whole, the major elements making up over 90% of our planet are iron, at about 35%.
35% iron.
Yeah, mostly in the core. Oxygen at 30%, surprisingly high, but it's tied up in minerals. Silica at 15%, and magnesium at 11%. Imagine a dense core of iron and nickel surrounded by layers of lighter silicate materials. This density-based arrangement is a direct result of how Earth formed through what we call the nebular accretion process.
From that swirling cloud of gas and dust.
Precisely. It gradually cooled, condensed, and differentiated based on density.
It's mind-boggling to think about the massive scale of these elemental distributions. And these elements, of course, combine to form the building blocks of our planet. Rocks.
Exactly. And while Earth boasts three main rock types, igneous, sedimentary, and metamorphic, let's focus on igneous rocks for a moment. These are the fire-formed rocks, created directly from cooling magma or lava. They tell a story about where and how they formed.
Okay.
We classify them primarily by their cooling location. Intrusive, or plutonic, rocks cool slowly underground, deep within the Earth's crust. This slow cooling allows for the formation of large, visible crystals, making them coarse-grained. Think of granite, with its distinct speckles of different minerals.
Right, you can see the crystals.
Yeah. Extrusive or volcanic rocks, on the other hand, erupt onto the Earth's surface and cool rapidly in contact with air or water. This quick cooling doesn't allow much time for crystals to grow, resulting in very small or even no visible crystals like the fine-grained basalt, which makes up most of the oceanic crust. It looks much more uniform.
So the same molten rock can create vastly different-looking rocks depending on how fast it cools. It's a powerful distinction. And this layering isn't just about rocks, but the very makeup of our entire planet from the outside in. Can you break down those main layers for us?
Indeed. To understand Earth's interior, we can think of it in two main ways. First, by its chemical composition. This gives us the traditional layers, the crust, the mantle, and the core.
Crust, mantle, core. Got it.
The crust is our thin, outermost skin, less than 1% of Earth's volume and mass. But even it has two types. The continental crust, which is thicker, around 40 kilometers on average, less dense, lighter, and mostly made of granitic rock. We sometimes call it silal for silica and alumina. And the oceanic crust, which is much thinner, around 5 kilometers, denser, and made of basaltic rock, sometimes called sima for silica and magnesium.
Okay.
Beneath the crust is the mantle, the thickest layer by far, forming about 83% of Earth's volume and 67% of its mass. It's a complex transitional zone, mostly solid rock, but capable of slow flow over geological time. And at the very heart is the core, our innermost layer, mostly iron and nickel, with a solid inner core and a liquid outer core.
And what about the other way we categorize it? Not by chemistry, but by how rigid or fluid it is, its mechanical properties.
Right, the second way to visualize Earth's interior is by its mechanical properties, focusing on rigidity or strength. Here, we define the lithosphere as the rigid outermost shell. This includes both continental and oceanic crusts, plus the uppermost, rigid part of the mantle, extending down to about 100 kilometers. This is absolutely crucial. The lithosphere is not a continuous shell. It's broken into these massive moving pieces we call lithospheric plate.
The tectonic plates.
Exactly. Beneath the rigid lithosphere lies the asthenosphere. This is a weaker, semi-molten, almost jelly-like layer within the upper mantle, extending down to maybe 300–400 kilometers. This layer contains minerals like olivine, which lose rigidity under sustained stress, making it somewhat plastic or ductile. This plasticity is what allows the rigid lithospheric plates to slowly drift or glide over it. It's like the plates are floating on this softer layer.
Okay, so the plates move on the asthenosphere.
Correct. Deeper still is the mesosphere, which corresponds to the more rigid lower mantle, down to about 2,900 kilometers. And then the core itself, which is sometimes called the perisphere or barysphere in this mechanical model.
This is where we get to the core of how our continents move and how mountains are formed through the incredible process of plate tectonics, which, as a theory, built on earlier ideas of a dynamic Earth. This idea of continents moving was pretty revolutionary at the time, wasn't it?
Oh, absolutely radical. When Alfred Wegener, who was actually a meteorologist, not a geologist, first proposed his continental drift hypothesis, CDT, back in 1912, the prevailing scientific view was that continents were fixed, static features.
They didn't move.
Right. Wegener suggested something completely different. That around 200 million years ago, all the world's land masses were joined together in a single supercontinent he called Pangaea. He envisioned it nestled mostly in the southern hemisphere, surrounded by a vast superocean called Panthalassa.
Pangaea and Pamplona.
Exactly. He theorized that Pangaea then began to split apart first into Laurasia to the north and Gondwanaland to the south, which then further fragmented into the continents we recognize today, drifting to their current positions.
And what kind of evidence did Wegener gather to support such a bold, seemingly impossible idea? It must have been met with skepticism.
Huge skepticism, but he built a compelling case with multiple lines of evidence. First, he pointed to the remarkable jigsaw fit of the continents, especially how the coastlines of South America and Africa look like they could snap together across the Atlantic.
Yeah, you could really see that on a map.
Then he found similar types and ages of rocks on continents now separated by vast oceans, hinting they were once connected. There is extensive evidence of ancient glaciation deposits called tillites found on continents like Africa, India, and Australia, which are now in tropical or subtropical regions. That suggested they were once located closer to the South Pole.
Glaciers in the tropics, only if the land moved.
Precisely. He also looked at paleomagnetism, the record of Earth's magnetic field preserved in rocks. It showed how the magnetic poles had apparently shifted relative to the continents over time, which made more sense if the continents themselves were moving. And perhaps most famously, he found identical fossils of land-dwelling creatures and specific plants.
Like Lystrosaurus.
Exactly, like the land reptile Lystrosaurus, the freshwater reptile Mesosaurus, and the plant Glossopteris found on continents now separated by thousands of miles of ocean. How could they have crossed? His conclusion: they lived on a united landmass.
That's quite a collection of clues. But he didn't have the how, right? The mechanism.
Yeah. That was the main sticking point for many scientists. Wegener couldn't provide a convincing physical mechanism for how the continents moved. Later, Arthur Holmes proposed the convection current hypothesis, suggesting that slow-moving convection cells within the Earth's mantle could provide the driving force. Heat from the core creates currents in the mantle, dragging the plates along.
Ah, the engine.
Sort of, yeah. Then, after World War II, with new mapping of the ocean floor, Harry Hess introduced the concept of seafloor spreading, SFS. He proposed that new oceanic crust is constantly being generated at mid-oceanic ridges where magma rises, and that older crust is being consumed or destroyed at deep ocean trenches called subduction zones.
So the ocean floor itself is moving, spreading out.
Exactly. The modern theory of plate tectonics brilliantly integrated Wegener's continental drift, Holmes's convection currents, and Hess's seafloor spreading, along with a wealth of new data, to give us our current, comprehensive understanding of Earth's incredibly dynamic surface.
It's a story of constant motion shaping the very face of our planet. Let's look at the incredible things that happen when these colossal plates interact at their boundaries. That's where the action is, right?
Absolutely. Plate boundaries are zones of intense geological activity, earthquakes, volcanoes, mountain building where much of Earth's drama unfolds. There are three main types. First, divergent boundaries.
Earth apart.
Exactly. Where plates move apart from each other. This allows magma from the mantle to rise, cool, and solidify, creating new crust. The most iconic examples are the mid-oceanic ridges, like the Mid-Atlantic Ridge, which is essentially a giant underwater volcanic mountain range where new seafloor is born.
And on land.
On land, divergent boundaries create rift valleys. The most spectacular example is the African Rift Valley. This massive continental rift, once thought by some to be a dyed arm of an ancient triple junction near Djibouti, has clearly reactivated, especially since around 2022. It's actively splitting the African continent apart.
You can actually see it happening.
Yes, you can see new fissures and faults opening up, like the recent Suswa Rift that appeared in Kenya. It's a slow process, but it's ongoing. This ongoing split is why it's so important to map and study the numerous unique lakes within the African Rift Valley, like Tanganyika, Malawi, and Turkana. They sit right within this active rift zone.
So, new land is being created where plates pull apart. What happens when these massive forces push together, convergent boundaries?
Right. When plates collide, we have convergent boundaries, and these are responsible for some of Earth's most spectacular and hazardous features. There are 3 subtypes, depending on the types of crust involved. First, when 2 oceanic plates converge.
Ocean meets ocean.
Yeah. The denser, or perhaps older and colder, and therefore slightly denser, oceanic plate subducts, meaning it dives down beneath the other one into the mantle. This subduction creates a deep ocean trench at the boundary. As the subducting plate descends, it heats up, releases water, which lowers the melting point of the overlying mantle wedge, generating magma. This magma rises to the surface, erupting to form volcanic archipelagos, linear chains of volcanic islands parallel to the trench. Think of the Aleutian Islands, the Mariana Islands, with the Mariana Trench, or the Kuril Islands in the Pacific. We also often get marginal seas like the Bering Sea or the Sea of Okhotsk, formed in the back arc basin behind these island arcs, and scraped off sediments form an accretionary prism or wedge.
Okay, lots happening there. What about ocean meeting continent, OC?
When an oceanic plate collides with a continental plate, OC, the denser oceanic plate always subducts beneath the lighter, more buoyant continental plate. Again, this creates a deep ocean trench offshore. The subducting oceanic plate generates magma, which rises through the continental crust, forming powerful volcanic mountain ranges along the edge of the continent. The classic example is the mighty Andes Mountains along the western coast of South America, formed as the Nazca Plate subducts under the South American plate. You also get accretionary prisms here, too.
And what happens when 2 continental plates, both relatively light and buoyant, crash into each other? CC convergence. Does one subduct?
When 2 continental plates converge, CC, neither is dense enough to significantly subduct deep into the mantle like oceanic crust does. Instead, the immense compressive forces cause the crust to buckle, fold, fracture, and thicken dramatically. It's like 2 cars crashing head-on. The metal crumples upwards. This process forms massive fold mountains. The ultimate example of this is the Himalayas, the world's highest mountain range, which continues to grow today as the Indian Plate relentlessly pushes north into the Eurasian Plate. The Alps in Europe are another great example of CC collision. These collisions are incredibly powerful, creating the most dramatic non-volcanic mountain landscapes on Earth and causing major earthquakes.
And the third type of boundary, where they slide past each other.
That's the transform boundary. Here, plates slide past each other horizontally, roughly parallel to the boundary line. Crust is neither created nor destroyed, but the friction between the sliding plates causes significant stress to build up, which is then released suddenly as earthquakes. The San Andreas Fault in California is probably the most famous example of a transform boundary.
From newly forming rifts to towering mountain ranges, these plate interactions are truly dramatic. But they also come with powerful, often destructive consequences, volcanoes and earthquakes, which you've mentioned. Let's dig into those a bit more.
Right. Most volcanoes aren't randomly scattered across the globe. They're strongly concentrated along these dynamic plate boundaries. A significant majority, around 70–80%, occur at convergent boundaries, especially subduction zones, OO and OC, where the process of subduction generates magma.
Makes sense, melting rock.
Exactly. A smaller percentage, maybe 15%, are found at divergent boundaries like mid-oceanic ridges and continental rifts, where plates are pulling apart and magma rises passively to fill the gap.
So where are the main hotspots globally?
Globally, we see 3 major volcanic belts. The most famous is the Circum-Pacific region, often called the Ring of Fire. It stretches around the Pacific Ocean basin and is home to the vast majority of the world's active and dormant volcanoes, linked to the numerous subduction zones there. Then there's the Mid-Atlantic region, primarily associated with the Mid-Atlantic Ridge divergent boundary. And the Alpine Himalayan belt, which runs through the Mediterranean and extends towards Southeast Asia, is mostly related to the collision between the African, Arabian, and Indian plates with the Eurasian plate.
And within these belts, some volcanoes are always active, others are just taking a nap, and some are done for good. How do we categorize them?
We classify volcanoes based on their recent activity level. Active volcanoes are those that are either currently erupting or have erupted in recorded history and are expected to erupt again. Barren Island in India's Andaman Islands is an example of an active volcano.
Yeah.
Dormant volcanoes are considered sleeping. They haven't erupted for a long time, possibly thousands of years, but they still have the potential to erupt again in the future based on their geological setting. Nakondam Island, also in the Andamans, is often classified as dormant.
Sleeping giants.
Potentially, yes. Then there are extinct volcanoes, which are considered very unlikely to ever erupt again. Their magma source is gone, or the tectonic setting has changed. Famous examples include Mount Kilimanjaro in Tanzania or Mount Kenya. The type of lava they erupt also matters a lot for hazard assessment running. Less viscous basaltic lava, like in Hawaii, tends to create gentler shield volcanoes, while thicker, more viscous andesitic or rhyolitic lava, common at subduction zones, can trap gases and lead to much more explosive eruptions from stratovolcanoes.
Volcanoes are just one way Earth releases its internal energy. The other, and often far more sudden and widespread, is through earthquakes. How do those work?
An earthquake's journey begins deep within the Earth at its focus, or hypocenter. That's the precise point along a fault where the rupture starts and the stored elastic energy is released. The spot on the Earth's surface directly above the focus is called the epicenter. That's usually what's reported in the news because it's the point of maximum shaking on the surface.
Focus deep down, epicenter on the surface.
Got it.
And depth matters.
Depth matters hugely for the intensity and type of damage. We classify earthquakes by how deep their focus is. Shallow focus earthquakes occur from the surface down to about 7,100 kilometers deep. Intermediate focus earthquakes are between 100 and 300 kilometers deep, and deep focus earthquakes can originate anywhere from 300 down to about 700 kilometers deep. Below that, the mantle material is generally too ductile to store and release energy as brittle fractures.
And where do the most dangerous ones usually happen? Shallow.
Generally, yes. Shallow focus earthquakes at plate boundaries can be incredibly violent. At oceanic-oceanic or oceanic-continental convergent boundaries, subduction zones, they're often linked with volcanic activity and can be very destructive. But perhaps the strongest shallow focus earthquakes in terms of sheer energy release often occur at continental convergent boundaries, like the devastating Bhuj 2001 and Latur 1993 earthquakes in India. This is because the immense compressive forces locking two continental plates together can lead to a greater buildup of stress over larger fault areas before they rupture catastrophically.
Okay, so shallow quakes are often the most damaging. What about intermediate and deep focus earthquakes? Where do they fit in? Are they only at subduction zones?
Yes, intermediate and deep focus earthquakes are indeed predominantly found at subduction zones, OO and OC convergent boundaries. This is where we encounter the critical Benioff-Wadati zone, named after the seismologists who discovered it.
Benioff-Wadati zone.
Right. Imagine this 3B planar zone where the cold, dense oceanic plate is diving down into the hotter, softer mantle. As it descends, it doesn't just smoothly slide, it bends, stresses, and breaks apart due to immense internal forces and high friction with the surrounding mantle material. It's within this descending slab, within the Benioff-Wadati zone, that intermediate and deep focus earthquakes originate.
So the slab itself is breaking deep down.
Exactly. A recent and stark example was the devastating New Year's Day earthquake in Japan in 2024 near the Noto Peninsula. Japan sits at the incredibly complex confluence of four major tectonic plates, the Pacific, Philippine Sea, Eurasian, and North American plates, making it one of the most seismically active regions on Earth. Many of its significant earthquakes, including deeper ones, manifest within these active Benioff-Wadati zones as the Pacific and Philippine Sea plates are forced beneath Japan.
So the deeper the plate goes, the more complex the seismic activity becomes. But earthquakes don't only happen at plate boundaries, do they? What about those that occur in seemingly stable areas, far from the edges of plates, like in the middle of continents?
You're absolutely right. Not all earthquakes are confined to the edges of plates. There are two other important settings. One is randomly distributed hotspots. These are areas where plumes of superheated magma rise from deep within the mantle, perhaps from the core mantle boundary, punching through the overlying plate to create volcanic and seismic activity far away from any plate edge.
Like Hawaii.
Hawaii is the classic example. Yellowstone is another continental hotspot. Along the mid-oceanic ridge system, you also find hotspots like Iceland, where the Atlantic ridge actually surfaces, allowing you to visually see the rifting between the Eurasian and North American plates, fueled by a hotspot beneath. Other examples include the Azores, Ascension, St. Helena, where Napoleon was exiled, Tristan da Cunha, often called the world's loneliest inhabited island. Many of these volcanic islands trace hotspot tracks. Mauritius and Reunion in the Indian Ocean are also hotspot related.
Okay, hotspots. What's the other reason for mid-continent quakes?
The second category comes from ancient fault lines within continents. As continents drift, collide, and rift apart over geological time, they develop internal cracks, rifts, and zones of weakness. These ancestral fault lines, which may have been inactive for millions of years, can sometimes be reactivated by present-day stress fields, often related to distant plate boundary interactions. Changes in stress can cause these old weaknesses to slip again.
So old wounds can reopen, seismically speaking?
Exactly. In India, for instance, the Narmada Rift Zone, associated with powerful historical earthquakes like those near Bhuj and Latur, is thought to be related to reactivated ancient structures. Regions like the Western Ghats and the Kutch area in Gujarat also experience seismicity linked to these reactivated ancient fault lines. It's a reminder that even seemingly stable parts of continents have a long, dynamic history recorded in their underlying structure, making them potentially earthquake-prone.
This raises an important question. If we know these events are inevitable, especially in high-risk places like Japan or parts of India, what can we do to protect ourselves and mitigate their impact? What lessons can we learn from countries that live with constant seismic activity?
Mitigation is absolutely crucial, and it heavily relies on robust earthquake engineering, particularly earthquake retrofitting for older buildings, and, critically, the strict development and enforcement of modern building codes for new construction. Japan, due to its location at that dangerous confluence of four major plates, is a world leader in this field.
How do they do it?
To understand the risk, consider the cake collapse analogy. Buildings without proper reinforcement, especially against horizontal forces, simply pancake or crumble during strong seismic waves, particularly the surface L waves that cause severe sideways shaking, essentially shaking the foundations out from under them. In Japan, their building codes are remarkably stringent and incorporate innovative engineering solutions. They employ several ingenious structural approaches. The Seishin structure focuses on basic structural reinforcement using advanced, often more flexible materials to maintain the building's integrity even during intense shaking, preventing brittle failure. The Keishin structure incorporates damping mechanisms, things like shock absorbers, or a central pendulum-like structure that absorb and dissipate the seismic energy, reducing the building's overall movement and minimizing sway.
Like shock absorbers in a car.
Exactly. And perhaps most impressively, the Seishin structure uses base isolation. Here, the building's entire foundation is literally separated from the ground using flexible layers, often made of rubber and steel bearings. This allows the ground to move violently beneath the structure during an earthquake without transferring the full force up into the building itself. The building essentially floats above the shaking ground.
That's incredible technology. How does that compare to other places?
Well, sadly, in many parts of the world, including seismically vulnerable regions in India like the Himalayas, building codes might exist on paper, but are often not strictly enforced due to cost, corruption, or lack of awareness. This tragically leads to significantly higher casualties and property damage in major earthquakes compared to places like Japan with rigorously applied codes. It highlights the critical importance of not just having codes, but ensuring they are actually followed.
This concept of working with nature's forces, designing buildings to accommodate shaking rather than just rigidly resisting it, is a powerful lesson. And speaking of powerful lessons in dramatic geological history, let's now deep dive into the unique story of India's physical landscape, which has been shaped by some truly monumental geological events, starting with a massive volcanic outpouring, #6, India's unique physiography and climate.
India's incredibly diverse landscape is a grand testament to immense geological forces operating over millions of years. A truly pivotal event in shaping peninsular India was the formation of the Deccan Traps.
The Deccan Traps. Heard of them. Massive lava flows, right?
Colossal is the word. This vast igneous province was born around 66 million years ago, right around the time the dinosaurs went extinct, possibly related. It happened when the Indian plate, drifting northwards, passed over the Reunion hotspot in the Indian Ocean. This triggered gigantic fissure eruptions, pouring out layer after layer of fluid basaltic magma.
How big an area are we talking about?
Huge. These traps cover a significant chunk of central and western India, something like 500,000 square kilometers today, and probably much larger originally. They include southern Malwa Plateau, large parts of the Western Ghats, especially the northern section, the Gur region of Gujarat, Kathiawar Peninsula, the Konkan Coast, Marathwada, Vidarbha, the Telangana Plateau, and northern Karnataka.
And this lava created specific soils.
Yes, crucially, this dark basalt, over millions of years of weathering, erodes to form India's incredibly rich black regur, or black cotton soil. It's famous for its high fertility and excellent moisture retention due to its high clay content. This makes it great for growing cotton, sugarcane, and other crops. However, that same water retention can sometimes lead to challenges with waterlogging or groundwater recharge in rain-fed agricultural areas if the underlying basalt layers are too dense and impermeable.
So that's where the iconic black soil comes from. But the Deccan traps were just the beginning of modern India's shaping, weren't they? 4 other massive events followed that really sculpted the land.
Absolutely. The Deccan Traps set the stage, but 4 subsequent transformative events truly defined India's modern geography as we know it. First, the formation of the Western Ghats. This dramatic mountain range rose primarily as the western edge of the peninsular block subsided or rifted away into the Arabian Sea, creating a steep fault scarp.
So it's like the edge of a tilted block.
Largely, yes. Second, a significant peninsular tilt occurred. The entire peninsula tilted gently eastward. This is fundamentally why most of India's major rivers originating in the western Ghats, like the Godavari, Krishna, and Kaveri, flow eastward across the entire peninsula to empty into the Bay of Bengal, not westward into the much closer Arabian Sea. Only a few shorter, faster rivers flow west.
Ah, that explains the river directions. Okay, third.
Third, the mighty Himalayan orogeny began and is still ongoing. This is the collision of the northward drifting Indian plate with the Eurasian plate, crumpling the crust and raising the world's highest mountains.
And fourth.
Fourth, the formation of the vast Indo-Gangetic Brahmaputra Plains. As the Himalayas rose, a large depression, or ford deep, formed to their south. This depression was then gradually filled in by the immense amounts of sediment eroded off the rising Himalayas and carried down by the Indus, Ganga, Brahmaputra rivers and their tributaries. These 4 events, superimposed on the Deccan Traps foundation, truly sculpted modern India.
It's a story of epic shifts and monumental creations. Let's start with the crown jewel of India's geography, the Himalayas, a mountain range that continues to grow and shapes so much of the country's climate and culture.
The Himalayas are, as you said, the direct and ongoing result of that continental collision between the Indian and Eurasian plates. The range is incredibly complex and diverse, but it can be broadly divided into the western and eastern Himalayas, each with distinct characteristics. The western Himalayas, stretching roughly from Nanga Parbat in the west towards the Nepal border, tend to rise in distinct parallel ranges or steppes.
Okay, steps.
Yes. You have the Great Himalayas, or Himadri, the highest range with peaks like Nanga Parbat. South of that lies the Middle Himalayas, or Himachal. This range is highly discontinuous and complexly deformed due to the intense compression. It includes famous ranges like the Pir Panjal, which forms the southern wall of the Kashmir Valley, and contains the Binihal Pass and the important Jawaharlal Nehru Tunnel, the Dalodhar Range, where picturesque towns like Pathankot, Dalhousie, and McLeodganj are located, and further east, the Mussoorie, Garhwal, and Kumaon ranges in Uttarakhand, and the Nagtibber Range. This is where many of India's famous hill stations are found.
Right, the holiday spots. And below those?
Below the Middle Himalayas are the Shivaliks, the outermost foothills. These are geologically much younger, essentially composed of uplifted and folded alluvial fans, gravel and sediment washed down from the higher ranges. They have a much lower average elevation, around 600 meters, maybe up to 1,500 meters.
So Great Middle and Shivaliks in the west. How do the eastern Himalayas closer to the northeast differ from this stepped pattern?
The eastern Himalayas, extending roughly from Sikkim eastwards through Bhutan and into Arunachal Pradesh, dominated by peaks like Kanchenjunga and ending near Namcha Barwa, are characterized by an incredibly steep, almost abrupt rise from the plains. The ranges are also much more tightly compressed.
So less defined steps.
Exactly. Due to even more intense compression in this region, the Middle Himalayas are largely absent or merged with the Great Himalayas. The Shivaliks rise almost directly after the Great Himalayas. The eastern Shivaliks themselves form distinct hills running east-west in Arunachal Pradesh, named after local tribes. the Dafala, Miri, Abor, and Mishmi ranges.
And this region has huge strategic importance.
Immense. The slopes here are extremely steep, rising rapidly to average elevations often exceeding 7,000 meters. The terrain is incredibly difficult to traverse and defend, posing significant challenges for infrastructure development and military logistics for India. This is why vital infrastructure projects, like the recently inaugurated Sela Tunnel, providing all-weather connectivity to Tawang, are so strategically crucial, and why China, which claims Arunachal Pradesh, often voices strong objections to such development near the border.
Got it. And further east, beyond the main Himalayan bend.
Further east, the Himalayas take a sharp southward turn at the Syntaxial Bend near Namcha Barwa. This range, running roughly north-south along the India-Myanmar border, is called the Purvanchal, or Eastern Hills. It comprises hills like the Patkai Naga Hills, Manipur Hills, and Lushai or Mizo Hills further south. It's important to note that sometimes Mount Dafa or Dafa Boom is mentioned in relation to Purvanchal, but geographically it's actually part of the Mishmi Hills, which belong to the Great Himalayan System in Arunachal, not the Purvanchal Range itself.
From the majestic peaks to the challenges they pose, the Himalayas are truly dynamic, and their formation had a domino effect, leading to the creation of India's vast and fertile plains, the breadbasket feeding millions.
Indeed. The relentless erosion from the rising Himalayas provided the truly immense volume of sediment, sand, silt, and clay that filled the foredeep to their south, creating India's northern plains. These plains are incredibly important agriculturally and are broadly divided into three major sections based on the river systems.
Okay, what are they?
First, the Transganga Plains, located west of the Aravalli Range. This vast, largely arid and semi-arid area includes Pakistan's Punjab province, India's Punjab state, Haryana, and large parts of Rajasthan, stretching down to the Kutch region. This region is historically famous for its doabs.
Doabs, land between rivers, right?
Exactly. Do means two, ab means water. It's the incredibly fertile alluvial land lying between two converging rivers. The Indus system created several famous doabs, mostly now in Pakistan, like the Sindh Sagar Doab, Indus Chelam, Chaj Doab, Chelab Chenab, Rachna Doab, Ravi Chenab. The parts most relevant to India are the Bari Doab, between the Ravi and Beas rivers, and especially the Bist Doab, between the Beas and Sutlej rivers, which form the heartland of India's Punjab. These doabs are exceptionally fertile agricultural lands.
So those are the western plains, fed by the Indus system. What about the central and eastern parts, dominated by the Ganga and Brahmaputra?
The Ganga Plains form the central and by far the largest part of India's northern plains. They stretch from the Yamuna River in the west all the way east to the Bangladesh border, covering most of Uttar Pradesh, Bihar, and West Bengal. They are often further subdivided into upper, middle, and lower Ganga plains based on elevation and river characteristics, but the entire region is characterized by deep, fertile alluvial soils deposited by the Ganga and its numerous tributaries like the Yamuna, Ghaghara, Gandak, and Kosi.
The heartland. And then the northeast.
Finally, we have the Assam-Brahmaputra Plains in India's northeast. These are relatively narrower plains flanking the mighty Brahmaputra River as it flows through Assam. The Brahmaputra is often called the sorrow of Assam, much like the Kosi is the sorrow of Bihar.
Why the sorrow of Assam? Flooding.
Exactly. As the Brahmaputra enters Assam, its passage becomes exceptionally constricted. It's squeezed between the eastern Himalayas, the Dafala, Miri, Abor, Mishmi ranges to the north, and the Meghalaya Plateau, Shillong Plateau, to the south. This dramatic narrowing, combined with the immense volume of water and sediment the river carries, especially during the heavy monsoon season, leads to frequent and devastating flooding across the plains, often impacting wildlife habitats like the Kaziranga National Park, famous for its one-horned rhinoceros population.
And there's a significant geopolitical angle to the Brahmaputra's water, isn't there? Especially concerning China. This makes this river even more critical.
Absolutely. It adds a layer of immense geopolitical significance and tension. China has a considerable strategic interest in Arunachal Pradesh, not just for territory, but crucially for water. A staggering 80% of the Brahmaputra's annual water volume, which China knows as the Yarlung Tsangpo in Tibet, actually originates from rainfall and tributaries within Arunachal Pradesh, rivers like the Siang, the main stem, Dibang, and Lohit joining just as it enters Assam. Only about 20% of its water volume comes from the Tibetan Plateau itself.
80% from Arunachal.
Yes. Given China's severe and growing water scarcity issues, particularly in its north, it views the abundant waters originating in Arunachal Pradesh as a crucial potential source for future large-scale water diversion projects. This water dimension significantly fuels its territorial claims over Arunachal Pradesh and makes the region an area of intense strategic interest and potential conflict regarding water resources for both nations.
The plains tell a story of rivers, agriculture, and huge geopolitical significance. But what about the other major landforms that define India's diverse landscape, particularly its ancient plateaus and hill ranges in the peninsula and the northeast?
Moving south from the plains, we encounter India's ancient plateaus and associated hill ranges. The Western Ghats, also known locally as the Sahyadris, form a prominent, almost continuous mountain range running parallel to the western coast of the Deccan Plateau for about 1,600 kilometers. They are a UNESCO World Heritage Site recognized for their exceptional biodiversity.
And they have distinct sections.
Yes, they are generally divided into 3 sections based on geology and characteristics. The northern Sahyadris, extending roughly from the Gujarat-Maharashtra border, starting near Nashik, with ranges like Satmala and Ajanta, southwards to about North Goa. This section is distinctive for its extensive capping of basaltic lava flows from the Deccan Traps. The central Sahyadris, stretching from North Goa down to the Wayanad region in Kerala, Tamil Nadu. This section is notably lacking the thick basaltic lava cover. The underlying older rocks are exposed, and the southern hills extending from Wayanad southwards down towards Kanyakumari near Point Calamere. This section includes famous ranges like the Nilgiris, where the eastern and western Ghats meet, the Anamalai Hills, with Anaimudi, the highest peak in South India, the Cardamom Hills, and the Pilani Hills.
Oh, the northern part, you mentioned ranges dividing rivers.
Yes, within the northern Sahyadris, several important east-west running hill ranges act as crucial watersheds, separating the basins of major east-flowing rivers. For instance, the Satmala and Ajanta ranges lie generally north of the Godavari River basin. The Balaghat range runs south of the Godavari but north of the Bhima River, a tributary of the Krishna, and the Harishchandra range lies south of the Bhima but north of the main Krishna River basin. These ranges dictate the drainage patterns across the northern Deccan Plateau.
So the Western Ghats are a clear, fault-bound edge of the peninsula, relatively continuous. How do they compare to the Eastern Ghats on the other side? They're often described as very different.
The Eastern Ghats are, indeed, a stark contrast. They are a series of highly discontinuous broken hill ranges running along India's eastern coast. They are geologically much older than the Western Ghats and have been significantly eroded down by the large east-flowing rivers Mahanadi, Godavari, Krishna, Kaveri that cut right through them on their way to the Bay of Bengal. They are much lower in elevation and lack the continuity of the Western Ghats.
Older and more broken up. Okay. And the northeast plateaus.
Finally, in the northeast, separate from the Himalayas, we have important plateau blocks. The most prominent is the Meghalaya Plateau, or Shillong Plateau. This includes the distinct Garo, Khasi, and Jintia hills arranged west to east, named after the local tribes. This plateau is famous for receiving some of the world's highest rainfall amounts, particularly around Masinram and Cherrapunji on the Khasi hills. Further east in Assam is the smaller Karbi Anglong Plateau. Geologically, these northeast plateaus are actually extensions of the main peninsular plateau of India. They were once connected but got separated by a large down-faulted gap called the Malda Fault, or Garo Rajmahal Gap, which was later filled in by sediments from the Ganga and Brahmaputra rivers. The separation created these unique, isolated upland blocks in the northeast.
From the ancient plateaus to the dynamic mountains, India is truly a geological marvel. But its climate, particularly the monsoon, is arguably its most defining feature, bringing life-giving rains, but also sometimes devastating floods. And its dynamics are far more complex than simply land heating up faster than the ocean, right? There's an upper air story.
You've hit on a critical point. While the older classical theory simplistically attributed the Indian monsoon solely to the differential heating of the landmass versus the ocean, creating a low pressure over land in summer, pulling in moist winds, this doesn't explain many key features like monsoon breaks or its pulsatory nature. The more accepted modern dynamic theory, often linked to the work of meteorologists like Yin and Flohn, sometimes called Yen's theory collectively, emphasizes the critical role of upper atmospheric circulation patterns.
Upper air dynamics, like jet streams.
Exactly. Central to this modern understanding is the subtropical westerly jet stream, STWJ. This is a powerful, high altitude, around 7 to 9 kilometers, sometimes higher, ribbon of wind blowing from west to east in the upper troposphere over the subtropics. During winter, as it encounters the massive barrier of the Tibetan Plateau and the Himalayas, with average elevations exceeding 5,000 meters and peaks much higher, the STWJ bifurcates or splits into two distinct arms. A northern arm flows north of the plateau over Central Asia, and a crucial southern arm flows south of the Himalayas, right over northern India, extending as far east as Assam.
So this jet stream sits over India in winter. How does that affect the monsoon's arrival in summer?
The position of the southern arm is absolutely critical. According to principles relating jet streams to surface pressure, like Druknes circulation theorem, a high-pressure system tends to form on the right side, poleward side, of the jet exit region, which in winter would be over Tibet, contributing to the cold, dry conditions there. Conversely, the area to the left, equatorward side, tends to experience divergence aloft, favoring low pressure at the surface, but in winter, the overall pattern keeps India relatively cool and dry under the influence of this jet. Now, for the summer monsoon to onset, this southern arm of the STWJ must crucially shift north of the Himalayas. This northward shift typically happens abruptly around late May or early June.
Why does it shift?
It's linked to the intense heating of the Tibetan Plateau in summer, which creates a strong thermal high-pressure system aloft, effectively pushing the jet stream north. Once the STWJ's southern arm moves north of the Himalayas, it allows the Intertropical Convergence Zone, ITCZ, that planetary belt of low pressure where the northern and southern hemisphere trade winds converge to migrate northward and become fully established over the heated landmass of northern India. Once this low-pressure trough, the ITCZ or monsoon trough, is established over India, it acts like a vacuum, effectively pulling in the moisture-laden southwest monsoon winds from the warm tropical oceans, Arabian Sea and Bay of Bengal, ushering in the rainy season.
So the jet stream has to get out of the way first. And what about those periods during the monsoon when the rain just stops for a week or two, monsoon breaks?
Exactly. Monsoon breaks are often explained by temporary southward shifts or weakening of the factors maintaining the monsoon. Sometimes the STWJ's southern arm might temporarily reappear over northern India, or the monsoon trough might shift northwards to the Himalayan foothills, effectively blocking the inflow of moist monsoon winds into the plains and causing a lull or break in the rainfall over much of the country. The monsoon isn't a continuous downpour. It comes in pulses, strongly influenced by these upper air dynamics.
This raises an important question. We hear about extreme weather events all the time, but how does this complex interaction of jet streams, the ITCZ, and maybe other weather systems manifest in those events, like the devastating floods we saw just last year in North India? Can this theory explain that?
It can offer a very strong explanation. A perfect and very recent example is the truly unprecedented and widespread flooding that hit Himachal Pradesh, Uttarakhand, and even caused the Yamuna River to flood parts of New Delhi in July 2023.
I remember that. It was shocking.
It was. What likely happened, according to this dynamic understanding, was a fascinating and destructive confluence of factors. During what should have been established southwest monsoon conditions, meaning the STWJ southern branch should have been well north of India, that southern branch, perhaps due to unusual meandering or waviness in the jet stream pattern globally, temporarily dipped southwards and reappeared over northern India.
The jet stream came back when it shouldn't have.
Effectively, yes. Now, this southward dip of the upper-level westerly jet stream during the monsoon season is known to sometimes steer western disturbances, those low-pressure systems originating in the Mediterranean Sea that typically bring winter rain to North India into the region even during summer. Usually, they pass further north in summer.
So a winter system arrived in summer.
Exactly. And here was the critical factor for the extreme flooding: a double boost of moisture. You had the abundant moisture already present due to the active southwest monsoon flow from the Arabian Sea and Bay of Bengal. Then, this moisture field interacted with the instability and additional moisture brought in by the unseasonal western disturbance, steered in by the misplaced jet stream. This convergence significantly intensified the rainfall far beyond typical monsoon levels, leading to those historic and tragic floods and landslides.
Wow. And the flooding in Delhi.
In urban areas like Delhi, while the heavy rain was the trigger, the severe flooding of the Yamuna floodplains was tragically exacerbated by decades of illegal construction and encroachment on the river's natural floodplain. These structures obstructed the river's natural flow path and significantly reduced its capacity to handle the unusually high volume of floodwaters coming down from the upper catchment areas. It was a powerful and devastating lesson in how global atmospheric patterns, regional weather systems, local topography, and human actions, like unplanned urbanization, can combine with catastrophic effect.
This fascinating intersection of global atmospheric patterns and local topography has profound effects, not just on rainfall, but on the very ground we stand on, the soils that form, and the vegetation that grows. Let's delve into India's soils and the rich tapestry of its vegetation, which are directly shaped by these geological and climatic forces we've discussed.
Absolutely. India's diverse physiography and climate have blessed it with an incredible array of soil types, each reflecting the parent rock, climate, vegetation, and time over which it has developed. Each has unique characteristics and agricultural potential.
Where do we start? The most widespread.
Probably alluvial soil. It's by far the most extensive and arguably the most fertile soil group in India, covering about 40% of the total land area. It's predominantly found in the vast northern Great Plains, deposited by the Indus, Ganga, Brahmaputra, and also in the deltas and coastal plains of major peninsular rivers like the Mahanadi, Godavari, Krishna, and Kaveri.
And there are types of alluvial soil.
Yes, it's broadly categorized based on age and location. Kadar is the new alluvial soil found in active floodplains. It's replenished annually by floods, making it extremely fertile, fine-textured, and rich in humus. Bangar is the older alluvial soil found on terraces above the flood level. It's generally less fertile than Kadar, often coarser, and may contain calcium carbonate nodules called kankar.
Okay, alluvial is key. What about that black soil from the Deccan Traps?
That's black soil, also known locally as Rigur or internationally as Vertizol. As we discussed, it forms from the weathering of the basaltic lava of the Deccan Traps. It's famed for its high clay content, which gives it excellent moisture retention capacity, vital for cotton cultivation, hence its other name, black cotton soil. It's also known for its self-plowing property. It swells significantly when wet and develops deep cracks upon drying, which helps in aeration. It dominates the Deccan Plateau region.
Right, and the reddish soils.
Those are red and yellow soils. These develop on crystalline igneous rocks like granite and gneiss, typically in areas of relatively lower rainfall, often on the periphery of the black soil regions in the peninsula, and also in parts of the northeast. They appear red due to the high concentration of iron oxides, especially when dry. They often look yellowish when they are in a hydrated form. They are generally less fertile than alluvial or black soils, often deficient in nitrogen, phosphorus, and humus.
So that covers the big three. What about other important types, maybe in harsher environments?
Laterite soil is interesting. It develops in regions with high temperatures and heavy seasonal rainfall, leading to intense leaching. Silica and lime are leached away, leaving the soil rich in iron and aluminum oxides. They harden significantly upon exposure to air, making them suitable for use as building bricks, hence the name laterite from the Latin word for brick. They are generally acidic and poor in nutrients, often found in patches on uplands in the Western Ghats, Eastern Ghats, and parts of the Northeast.
Okay, and deserts.
In arid and semi-arid regions like Western Rajasthan, you find arid soil. As the name suggests, it's sandy in texture, often saline due to high evaporation, leaving salts behind. Very low in humus and moisture, but can be made productive with irrigation.
Mountain soils.
Forest soil, or mountain soil, is found in hilly and mountainous regions, particularly the Himalayas. Its characteristics vary greatly depending on altitude, slope, and vegetation cover. Soils on lower slopes and valleys tend to be deeper and richer in humus, while those on steep upper slopes are often thin and immature.
Any others? Salty soils. Peaty soils.
Yes, saline or alkaline soils, known locally by names like Re, Kalar, Usar, occur in arid and semi-arid regions, often due to poor drainage, waterlogging, or overuse of irrigation leading to salt accumulation at the surface. They are infertile, and peaty soils form in areas with heavy rainfall and high humidity, leading to accumulation of large amounts of dead organic matter. They are rich in humus, often black, heavy, and highly acidic, found in parts of Kerala, coastal Odisha, and West Bengal.
So many types. And the texture matters too, right? Say sandy, clay, loam.
Absolutely. Fundamentally, all soils are a mixture of mineral matter from weathered rock, water, air, and organic matter, humus. Soil texture refers to the relative proportion of different-sized mineral particles. Coarse-grained sand, particles 0.003 millimeters to 2 millimeters, medium-grained silt, 0.0002 millimeters to 0.02 millimeters, and very fine-grained clay, less than 0.0002 millimeters. Texture dictates things like drainage and water holding capacity. Sandy soil drains poorly but holds a lot of water due to strong capillary action. Loamy soil, which has a balanced mixture of sand, silt, and clay, is generally considered ideal for agriculture because it retains adequate moisture while also allowing good drainage and aeration. Soil structure, how these particles clump together, is also crucial.
The soil is literally the foundation of life and agriculture, and it, along with climate, dictates what kind of natural vegetation thrives across India, creating incredibly diverse ecosystems from deserts to rainforests. Can you walk us through the main vegetation belts?
Certainly. India's natural vegetation is incredibly diverse, closely linked to variations in rainfall, temperature, altitude, and soil type. We can broadly classify it into several major types. Let's start with the lushest, tropical wet evergreen forests.
Rainforests.
Essentially, yes.
Mhm.
These thrive in areas receiving very high rainfall, typically over 250, 300 centimeters annually, with a short dry season. You find these dense forests on the windward slopes of the Western Ghats, parts of the Andaman and Nicobar Islands, and stretches of the Northeast, including the upper reaches of Assam, Meghalaya Hills, and the foothills of the Eastern Himalayas, like the Dafala, Miri, Abor, Mishmi Hills, and Parvanchal. They're characterized by tall trees, often exceeding 60 meters, forming a dense, multi-layered canopy that prevents sunlight from reaching the ground. They have broad leaves and harbor incredible biodiversity. Mahogany, ebony, rosewood are typical trees.
Okay, the densest. What about slightly less wet evergreen?
There's also tropical dry evergreen forest found in areas with moderate rainfall, around 100-200 centimeters, but a distinct dry season, notably along the Coromandel coast of Tamil Nadu, which gets rain mainly from the retreating northeast monsoon.
And then the vast green belt across much of India, the deciduous forests where trees shed their leaves.
Right. The most widespread forest type in India is tropical moist deciduous forest. These occur in areas receiving rainfall between 100 and 200 centimeters annually. They cover a huge swath of the country, forming a sort of green belt influenced by both the Bay of Bengal and Arabian Sea monsoon branches. These forests are commercially very important.
What kind of trees are key here?
Two iconic trees dominate different regions. Teak, sagwan, is highly valued for its timber, is relatively drought-resistant, and is dominant in the southern and central parts of this belt. Sal is another important hardwood, requires cooler conditions and more consistent rain, and tends to dominate in the northern and eastern parts, like Jharkhand, Odisha, Chhattisgarh. You find mixed zones in places like Madhya Pradesh and eastern Maharashtra. Sandalwood, chandan, prized for its aromatic wood, is also very prominent in the southern parts of this belt, especially Karnataka. Other common trees include mango, mahua, and bamboo.
Okay, and drier deciduous.
As rainfall decreases further, between 70 and 100 centimeters, the moist deciduous forests transition into tropical dry deciduous forests. Trees here are generally shorter, and the forest is less dense. Teak and sal might still be present, but other species adapted to longer dry seasons become more common. This belt covers large parts of the peninsula and the plains of UP and Bihar.
Then below 70 centimeters rainfall.
Below about 70 centimeters, you get tropical thorny forests and scrubs. These are found in the semi-arid regions of Rajasthan, Gujarat, Haryana, Madhya Pradesh, and the rain shadow areas of the Deccan. Vegetation consists mainly of thorny trees like acacia, bevel, kikar, palms, euphorbias, and cacti, adapted to conserve water.
Then there are mountain forests and mangroves.
Yes. Montane forests show dramatic changes with increasing altitude, mirroring the latitudinal vegetation belts. In the Himalayas, you go from tropical-subtropical deciduous at the foothills through temperate broadleaf forests like oak, chestnut, then temperate coniferous forests, pine, deodar, fir, spruce, up to alpine grasslands, meadows, or bugyals, and finally tundra vegetation near the snowline. And mangrove forests are specialized tidal forests found in coastal deltas, estuaries, and creeks, where trees are adapted to survive in saline, waterlogged conditions with stilt roots, pneumatophores, for breathing. The Sundarbans Delta is the largest mangrove ecosystem in the world.
From dense rainforests to arid thorny bushes, India's flora is incredibly diverse. And beneath this rich biodiversity, and shaped by the geology we discussed, lies another form of wealth. Its mineral resources, which fuel its industries and drive its economy. Where are the main mineral belts?
India's mineral resources, while diverse, show significant concentration in certain regions, primarily associated with the old crystalline rocks of the Peninsular Plateau. We can identify three broad belts: the Northeastern Plateau region, covering Chotanagpur Plateau and Jharkhand, Odisha Plateau, West Bengal, Chhattisgarh. This is the richest mineral belt, particularly for iron ore, coal, manganese, bauxite, mica. The Southwestern Plateau region, Karnataka, Goa, contiguous Tamil Nadu uplands, Kerala, rich in iron ore, manganese, limestone, bauxite. And the northwestern region, along the Aravalli Range in Rajasthan and parts of Gujarat, known for non-ferrous metals like copper, zinc, lead, as well as building stones like sandstone and marble.
Okay, those are the belts. Let's look at some key minerals that power the country and where India stands globally. Iron ore.
For iron ore, the backbone of modern industry, Australia is currently the world's leading producer. India is a significant global player, usually ranking among the top 5 producers. Within India, Odisha holds the largest reserves by far, followed by Jharkhand, Chhattisgarh, Karnataka, and Goa. Production leadership can shift, but Odisha, Chhattisgarh, Karnataka, and Jharkhand are the main producers.
And types of iron ore matter.
Yes. The best quality ores are magnetite, F304, which is black and has the highest iron content, around 70%, and excellent magnetic properties. And hematite, Fe203, which is reddish and the most important industrial ore, with 60–70% iron content. India has large reserves of high-grade hematite, especially in the eastern states. Inferior ores like limonite and siderite are also found, but are less utilized.
What about manganese, used in steel?
Manganese is crucial for making steel alloys. It imparts strength and hardness, and also used in chemicals, batteries, paints. Globally, China and Australia are major players. In India, Odisha again boasts the highest reserves, followed by Karnataka, Madhya Pradesh, MP, Maharashtra, and Andhra Pradesh. Production is led by MP, Maharashtra, and Odisha. Key districts in MP include Balaghat and Chhindwara.
And what about some of those less common but increasingly important metals that are vital for modern technology? Nickel, cobalt.
Good question. Nickel, essential for stainless steel, corrosion resistance, and various alloys, like those used in high-temperature exhaust systems, sees Indonesia and the Philippines as world leaders. In India, a staggering 92% of the known reserves are concentrated in Odisha, particularly in the Sukinda Valley associated with chromite deposits. The remaining reserves are scattered in Jharkhand, Nagaland, and Karnataka. Production, however, is still very limited.
And cobalt, critical for batteries.
Cobalt has become incredibly strategic due to its use in rechargeable lithium-ion batteries, powering everything from smartphones to electric vehicles. The Democratic Republic of Congo, DRC, absolutely dominates global production, accounting for over 70%. This overwhelming concentration, unfortunately, also brings significant ethical concerns regarding mining practices, including widespread reports of dangerous conditions and child labor, which is a serious global issue the tech and auto industries are grappling with. India has very limited cobalt resources, mostly associated with nickel and copper ores in Odisha, Jharkhand, and Rajasthan.
Okay. Chromium, bauxite, copper.
Chromium, used mainly for producing stainless steel via ferrochrome, electroplating, alloys, and pigments, sees South Africa holding the lion's share of global reserves, followed by Kazakhstan and Turkey. India has significant reserves, again heavily concentrated in Odisha's Sukinda Valley, making it a major global producer of chromite ore. Bauxite, the primary ore of aluminum, is abundant globally, with Australia being the top producer, followed by Guinea, China, Brazil, and India. India has large reserves, with Odisha being the leading state by a huge margin, followed by Gujarat, Jharkhand, and Maharashtra. Copper, an excellent electrical conductor vital for wiring and electronics, sees Chile as the undisputed world leader in production, followed by Peru and China. In India, Rajasthan holds about 50% of the reserves, particularly in the famous Khetri-Singana belt in Chunchunu district and also in Alwar and Bilwar districts. However, Madhya Pradesh, with about 24% of reserves, is currently the #1 producer, primarily from the large Melanchand open pit mine in Balaghat district. Jharkhand also has significant copper deposits. It's worth remembering that the very stainless steel we use every day is typically an alloy composed of iron, plus varying amounts of chromium, usually 10–20%, nickel sometimes, and small amounts of manganese and copper.
These minerals fuel our industries and build our infrastructure. But agriculture remains the backbone for millions in India, employing a huge part of the population. Let's look at some key agricultural industries that feed the nation and contribute globally. Sugar, tea.
Absolutely. India's agricultural sector is vast and vital. The sugar industry is the second largest agro-based industry in India after cotton textiles. India is consistently one of the world's largest producers of sugarcane and sugar, often vying with Brazil for the top spot in sugarcane production and usually second in sugar production.
Where is it concentrated?
Traditionally, the sugar belt of India was considered to be in the subtropical north, particularly Uttar Pradesh, UP, and Bihar. UP remains the leading producer of sugarcane and sugar, especially in districts like Meerut and Shamli. However, the industry has significantly shifted southwards to tropical regions in recent decades. States like Maharashtra and Karnataka now have higher yields per hectare and longer crushing seasons due to better climatic conditions for sugarcane. So, while UP leads in total production, Maharashtra, Karnataka, Tamil Nadu, Gujarat, Andhra Pradesh, Telangana, Punjab, Haryana, Bihar, Odisha, and Madhya Pradesh are all significant sugarcane and sugar producers.
Okay, and tea. India's famous for tea.
Indeed. The tea industry is another major agro-based industry. India is the largest consumer of tea globally and typically the second largest producer after China, but it remains the world's largest producer and consumer of black tea.
Where is it grown?
Tea cultivation requires specific conditions, warm temperatures, high rainfall distributed throughout the year, acidic soils, and well-drained slopes. It's grown commercially in about 16 states, but around 95% of the total production comes from just 4 states. Assam, the undisputed rank 1 producer, famous for strong black teas. West Bengal, especially Darjeeling, known for high-quality aromatic teas in the Doors region. Tamil Nadu, primarily in the Nilgiris, and Kerala.
And coffee, another global beverage commodity where India plays a significant role, particularly in Asia.
Yes. For coffee, India is the third largest producer and exporter in Asia, though much smaller globally compared to giants like Brazil and Vietnam. India grows both major varieties. The high-quality, milder Arabica, which fetches higher prices, and the stronger, more robust Robusta. Robusta actually dominates Indian production now.
Where is coffee grown in India?
Coffee cultivation is heavily concentrated in the hill tracts of South India. Karnataka is the undisputed leader, accounting for around 70% of India's total coffee production. Regions like Kodagu, Chikmagalur, Hassan, Kerala, especially Wayanad, and Tamil Nadu, Nilgiris, Kodaikanal, account for most of the rest. Coffee in India is unique as it's typically grown under shade trees, which is considered more sustainable and beneficial for biodiversity.
Interesting. What about pulses, essential protein source?
Pulses, dal, are incredibly critical for nutrition in India. India holds the unique position of being the world's largest producer, consumer, A&D importer of pulses. We grain a lot, but our consumption is so high we still need to import significantly.
Which types are grown?
A wide variety. They are grown in both Kharif, monsoon, and Rabi, winter seasons. Major Kharif pulses include arhar, turpigeon pea, moom, green gram, and urad, black gram. Major Rabi pulses include gram, chana chickpea, masoor, lentil, and peas. Rabi pulses actually account for about 60% of total production, with gram being the single most important pulse crop.
And top producing states?
Madhya Pradesh has consistently been the top pulse-producing state in recent years, followed by states like Rajasthan, Maharashtra, Uttar Pradesh, and Karnataka. Pulses are also important because they are legumes and fix atmospheric nitrogen, improving soil fertility.
Right. Lastly, oilseeds for cooking oil.
Oilseeds are another vital agricultural sector, crucial for edible oils. India witnessed a yellow revolution in the 1980s and 90s to boost oilseed production. 9 major oilseeds are cultivated: groundnut, peanut, rapeseed mustard, soybean, sunflower, sesame till, castor seed, linseed, niger seed, and safflower. The first 7 are largely edible, while castor and linseed have more industrial uses.
What conditions do they need?
Conditions vary, but generally they require moderate temperatures, 15-30 degrees C, relatively low rainfall, 30 to 75 centimeters, and well-drained loamy to clayey soils. They are grown across different seasons.
And are we self-sufficient?
Despite being one of the largest producers, India is also one of the world's largest importers of edible oils, particularly palm oil, soybean oil, and sunflower oil, to meet its huge domestic demand. Bridging this gap remains a major policy focus.
Which states are the biggest producers?
Around 70% of India's total oilseed production comes from just 4 states: Rajasthan, especially for mustard; Gujarat, strong in groundnut and castor; Maharashtra, soybean, groundnut, sunflower; and Madhya Pradesh, dominant in soybean, also mustard. Rajasthan and Madhya Pradesh are particularly important in terms of both production volume and the area dedicated to oilseed cultivation.
This overview truly paints a picture of India's incredible agricultural diversity, feeding its vast population and contributing significantly to the global economy. It's a complex, living system, deeply intertwined with the geology and climate we've explored. #outro. Wow, we've truly covered some immense ground today, haven't we? Feels like we've spanned the entire planet and zoomed right back into specific fields in India.
We certainly have.
So what does this all mean? We've journeyed from the Earth's fiery core way out to the wispy clouds, explored the powerful currents driving our oceans, and mapped the very foundations of India's unique geography and geology, all the way to the food on our plates. It's a testament to the sheer volume of interconnected knowledge that defines our planet and how everything, the rocks, the air, the water, the life, our activities, is fundamentally linked.
It truly is. The aha moments from this deep dive, I hope, really underscore that profound interconnectedness of all these geographical elements. From the slow, majestic dance of plate tectonics shaping continents over millions of years, to the intricate atmospheric dynamics dictating our monsoons season by season, this entire complex system is in continuous dynamic evolution.
Always changing.
Always. And this raises an important question for all of us, doesn't it? How can understanding these fundamental processes of our planet, from geological forces to atmospheric movements, from soil formation to water cycles, how can this knowledge better equip us to navigate the escalating challenges of climate change, resource management, and sustainable development in the future? How can it help us become better stewards of this incredible dynamic home?
That's a powerful thought to leave with. The Earth is constantly changing, and our role in understanding and adapting to those changes and minimizing our negative impacts is more important than ever. What aspect of this deep dive, our curious listener, will you explore next? We hope this journey has sparked even more questions and a deeper appreciation for our amazing complex planet.
Absolutely.
Thank you so much for joining us on the deep dive. Until next time, stay curious.